I thought I would cover not only a little bit about KamLAND and our work on KamLAND, but at a sort of a higher level than who did what on the experiment, but also a little bit about how Stuart was such a longtime friend, and perhaps try to offer a little bit of insight, speculative insight perhaps, into some of the things that happened a little below the surface with Stuart. So again, I'll just quickly review. I talked a little about this last night at the dinner. Long history with Stuart. It began at Princeton when we were both interested in second-class currents, and I was a student. He went on to Stanford, and I went to Argonne to do my thesis experiment with Jerry Garvey. But we started working on this boron-10 parity violation experiment. And I told you the story about him calling and inviting us over to the bar at the Holiday Inn all the time. And then, again, when I was at Caltech and he went back to Argonne, as Jerry Garvey relayed yesterday, we were studying neutrino oscillations at Los Alamos. So we worked for many years, and then more recently, when he was at Berkeley and I was still at Caltech, we began working on KamLAND. You can see that we were not only mounting the phototubes in the experiment, we were schlepping them around all over the place. So let me pick up the story, since I want to kind of give you the sort of high-level physics view of how we got into some of this. And I also like to bring in people from Caltech that I knew, like Willie Fowler from the old days. This is obviously before I even started doing physics, maybe even a little before Stuart. And when Ray Davis turned on his experiment in 1967, when he was trying to detect the solar neutrinos in the Homestake mine, a famous experiment that he eventually won the Nobel Prize for, he said, "Dear Willie," this is a letter that he wrote, "I do have a preliminary result from our first good run. The limit is quite low. Please regard these results as very preliminary. There are several points that must be checked before we are certain this is a bona fide observation. I will collect another sample in September. We are ready now. Turn on the sun." And so, and of course, it's in the ensuing years, there were all these measurements that indicated that the flux of solar neutrinos was significantly below the standard solar model calculation. Subsequent history with neutrinos, many things developed, and it was a nice subject, but it looked kind of like a normal business. They were able to show that the electron and muon neutrinos were not exactly the same as studied in accelerator-based production experiments. And around 1980, as other people mentioned yesterday, there was a tremendous interest in dark matter, and that perhaps an economical solution to the dark matter problem would be that neutrinos had a mass, and you could kind of put all of that together and would be a nice solution. But otherwise, there was not much of a role for the neutrinos in the world of particle physics, and that led, apparently, reportedly, Feynman to the quote, "All you have to do is imagine something that does practically nothing. You can use your son-in-law as a prototype." So it's a bit of a dated quote, but it's kind of a classic Feynman. I'm not sure it's actually correct, but found it several places, but it sounds good. Anyway, of course, we all know in 1998, things changed quite a bit when the Super Kamiokande experiment in Japan reported the evidence for neutrino oscillations in the atmospheric neutrinos. And everyone's familiar with this. I don't think I need to go into it, but it changed things considerably, and that's led to a lot of impetus to perform new experiments in neutrino oscillations. At that point, of course, we knew, although the tau neutrino had not actually been discovered yet, but we knew about the tau lepton, that there would be 3 neutrinos, and that there would be a mixing matrix, and that the Super K atmospheric neutrinos determined one of the 3 angles in this neutrino mixing matrix, and that there was it was then speculated, of course, that the solar neutrino deficit was related to oscillations with the other angle that of course, was the MSW matter-dependent effect, but that remained to be resolved. And so that's when the KamLAND experiment was first proposed by Itsuto Suzuki, as he mentioned yesterday, and our US collaborators got involved. The idea was to use the power reactors in Japan as a source of anti-electron neutrinos from neutron-rich fission products. You can detect them with the inverse beta decay reaction, and you can measure not only the flux, but the energy spectrum of these anti-neutrinos. KamLAND was a big leap from what had been done before. There were many reactor experiments, many of them searching for neutrino oscillations during that period of the 1980s and so forth. But KamLAND was a big jump in the baseline, and therefore the reactor power times target mass that you needed. And so you needed a very large target mass. We ended up with a kiloton of liquid scintillator, and so that also meant we had to go much deeper underground than the previous experiments to be able to make this measurement with comparable statistical precision. So KamLAND, of course, was in Japan, and the reason was at the time they were running something like 56 reactor cores at many power stations throughout Japan. And as someone mentioned earlier, these are generally located on the coast where you have water cooling available, and KamLAND was located at the Kamioka mine, sort of in the center here in the mountains. And so you can imagine that the closest reactors give you the largest flux of neutrinos, since there's even without oscillations, you have the 1/r² dependence. And so an important point is if you make a plot of the expected neutrino flux as a function of the baseline of the reactor, the distance to the reactor, you get a plot that looks like this. So there's a very large peak, just short of 200 kilometers, 180 kilometers, but there's a tail and lots of other things. And so it's not like there's a single source at a single distance. All right, we'll come back to that. Nevertheless, you can see that there's a very strong peak in this plot. As we were building the experiment, more, of course, in the ensuing years since Ray Davis, more solar neutrino results came out. And during this whole period, there were many, many global fits to all of the solar neutrino data that led to plots like this. And there were two significant islands that would be solutions to the solar neutrino problem, called the small mixing angle solution, where the angle was really quite small, and the large mixing angle solution, where the angle was large. And I remember over many years, Stuart commented quite a bit and emphasized that, well, most particle physicists, since the CKM matrix involves small angles, most particle physicists would tend to favor this small mixing angle solution, particularly theorists. The implication meaning that perhaps they have less imagination than the others, but he strongly felt that, gee, this is, and I think that under the surface, since Stuart, as we know and have emphasized over the last day or so, liked to measure nothing, KamLAND could see this an effect in neutrino oscillations if the LMA was the correct solution. But if SMA was the correct solution, you wouldn't see anything unusual at all, although you would see neutrinos. And so perhaps he really thought that the most likely situation was that we would measure nothing and SMA was the answer. And maybe that's really why he was doing this, but I don't know. People talked yesterday, Atsudo talked about the KamLAND, how it got built in detail. I took this, this is actually Stuart's slide from a couple of years ago, and many of us have different versions of this. We like to talk about Shinkansens or fast track, and KamLAND was really built on a very fast time scale compared to what we're normally used to, especially in the US. A lot of that had to do with the Japanese funding was very fast, and they were able to do things and expedite things. For the US, of course, I think many people have talked about Joyce's support, and I think actually the advanced funding from Berkeley that got us to Lord, hell no, that's all public stuff, isn't it? Was facilitated by Joyce to a large degree, and I think that helped us a great deal in keeping the schedule. We didn't quite get our results before Snow, who reported finding the missing solar neutrinos in 2002, measuring the neutral current process, which of course, this measures the sum of all flavors of neutrino. And for the first time, Snow was able to show that actually if you add up all the flavors of neutrino by measuring this neutral current process, that you actually get agreement with the standard solar model calculation, which indicates that there's clearly a flavor transformation process associated with the solar neutrinos. And so then, shortly after that, in 2003, we ran for about a little less than 1 year with KamLAND and came out with our first result, which is shown here. This is the measurement at the largest baseline of all the previous reactor experiments. This dotted curve is the result of one of those global fits, a large mixing angle solution that you see comes very, very close to our measurement. And so one is inclined certainly to believe that this measurement is confirming this picture quite well. So we're in the situation where Stuart fails to measure nothing. He actually saw neutrino oscillations, a very significant effect, but he still got it right. It was not the small mixing angle. I don't think he was actually disappointed, but it's interesting to speculate on that. Of course, here's the energy spectrum we measure. This is a later version with better statistics and better understanding of the backgrounds and so forth. And you can see that the spectrum is indeed distorted compared to what one would expect from calculations of the reactor spectrum. And then, of course, people, particularly our Japanese colleagues, first produced this plot. And I remember quite distinctly that there was a phone conference call where this was first presented to us by our Japanese collaborators. And many of us thought, wow, that is quite a stunning plot. That's an iconic plot that will make the textbooks. I mean, wow. But Stuart was not happy. Stuart was not happy because he thought the plot was somewhat unscientific. And the reason it was unscientific is to make this plot, you need to do this, you need to rebin the data in this variable L0 over the neutrino energy. I previously showed you the number of events as a function of neutrino energy. This is now plotted as a function of L0 over the neutrino energy. And there's really no mathematically precise way to define L0, right? So I showed you the distribution of L's in that plot earlier, and you're inclined to think of, the median, the mean, all kinds of moments in all kinds of ways, but none of them really is a defensible way to define this L0. Nevertheless, I think however you defined it, whether it's 180 or 200 kilometers or whatever, it's an intriguing and powerful way to present the data. And many of us had this positive emotional reaction, and Stuart was quite insistent that no, this is not a scientific plot. We should not have it in the publication. But in later years, of course, afterwards, Stuart showed this plot frequently and proudly. So I think, I remember many emails going back and forth about how because it's a Fourier decomposition problem, and how do you find the fundamental frequency in a funny spectrum like that? And anyway, we had a great time talking about it. But eventually he came around, realized that this was just a powerful way to display the data, and very convincing. And of course, you get very precise measurements of the delta M squared, and combining with the solar neutrino measurements, particularly Snow, you get very precise, fairly precise measurement of the theta 1,2 variable. So then we have back to the neutrino matrix, the mixing matrix. We now have this angle and we have this angle checked off. And there's one more angle, theta 1,3. And at this matrix element here with a sign of theta 1,3 multiplies the phase factor associated with CP violation in the neutrino sector. So it's very important. It was the next step was to find this theta 1,3. After a few months of people, a lot of people started getting interested in this back in 2003 or 4, and it was realized that if theta 1,3 is small, you're going to need to do a higher precision technique, and so you'll need to measure at the oscillation maximum the flux at what's called the far site, and you'll need a measurement at a nearer site to normalize the reactor flux. The reactor flux is typically known to 3% or so, at least that's the thinking from the calculations, and that if theta 1,3 is actually 1 or 2%, you better somehow have another way of canceling out the reactor flux. And this was the method that many people had finally settled on. And it was first proposed by, what was the fellow's name? Mikhailov, I think? I should have put it on this slide. But it's a very nice idea. And so a variety of searches were on to find a site. And this is interesting because Stuart, it was mentioned earlier today that Stuart was interested in this Diablo Canyon site in California. And I remember we went to a lunch with the vice president of PG&E, and I still have the presentation that we showed him and everything. We had a very nice lunch, but he was completely uncooperative. It was very clear we were never going to get to first base at Diablo Canyon. Stuart came with us to China and looked at the Diablo Canyon site. Here he is picking up rocks to bring back to Berkeley to find out, we have people analyze what kind of rock was there that we'd have to tunnel through to do the experiment. And so he was quite interested in this for a while. People have talked about how various reasons why Stuart didn't pursue Theta 1,3, particularly in China, but I'll come back to that with perhaps a different take on it. So there were 3 experiments actually mounted to measure Theta 1,3 with reactor neutrinos. One called the double show experiment at the show site in France, and one in Korea, the Reno experiment, and our experiment that I worked on, other people from Berkeley here, the Taipei experiment in China. This was our collaboration. You see it became quite large, over 240 collaborators, kind of split evenly between Asia and North America with a little bit of European participation. The layout of the site is shown here. The reactors are shown as these black dots, and there were 3 pairs of reactors, and they were separated by a significant distance. This is about 1 kilometer, and so we needed near sites to be able to monitor the flux at each of the reactor groups, and then a far site where we had more detectors to try and measure the flux there and find the reduced flux associated with a small Theta 1,3. We began in 2011 with the original plan was to have 2 detectors, and 4 detectors, total of 8. And a couple of the detectors were a little bit delayed, and we wanted to get running, particularly because we knew the Reno people were starting to run, and we didn't want to get too far behind. So we started with this configuration of 6 detectors. This is what our detectors looked like. Actually, the Reno detectors, double show detectors, are not too different. It's 20 tons of gadolinium-loaded liquid scintillator and a gamma catcher with normal liquid scintillator and mineral oil buffer outside with 192 photomultiplier tubes. It gave us 7.5% energy resolution. Lots of calibration things that I worked on, for example, that were essential to verify that the detectors at the near and far sites actually had essentially identical efficiencies to a high accuracy, which if you're going to measure this ratio and cancel out the efficiencies to get the survival probabilities for a small Theta 1,3, that's quite important. So in March, after running off only 3 months, we were able to report a fairly sizable deficit at the far site relative to expectation from the near sites of about 6% that led us to report that there was a large Theta 1,3. And so perhaps now we know why Stuart moved on from Theta 1,3. there was actually likely something there. Maybe, you know. And, you know, so going back to his true self, inner self, he wanted experiments more likely to find nothing, and we've heard something about that. But anyway, we know that there are other aspects to his decision, but perhaps there's something under the surface there. More recently, last year, we updated our result in July, and here's our rate-only analysis and our result for sine squared 2 theta 1 3 from that. And we also now see we report an energy spectrum distortion where there's a clear difference in the distortion at the near sites and the far sites, as one would expect with oscillations. And that allows us to do a simultaneous fit to both the mixing angle and to the delta M squared. This comes out very close to what's measured in the Minos experiment at Fermilab. So this is all starting to hang together quite nicely. In fact, I think you can see the Minos result is this dashed line here, and this is our measurement. So we're actually kind of following a program. This will be familiar to Boris. Theta 1 3, the last mixing angle. We now have it from the reactor program. CP violation, leptogenesis. There are accelerator experiments working on that and being built in the future to address that. Absolute mass scale, we heard about this from Hamish Robertson. Mass hierarchy. There are accelerator experiments and reactor experiments. We heard about this from Yuri this morning. And there's the question of whether the neutrino is its own antiparticle. Is it a minor particle that would lead to neutrinoless double beta decay? And this program is something that we owe to a very influential report written just about 10 years ago now, co-chaired by Stuart and Boris Kaiser, who's the chair of this session. So we're all kind of marching to the tune that Stuart and Boris, I mean, it's still in progress. It's really quite amazing. When we went into the snowmass process this last year, and I had to get up at one of the workshops and say a few things, I reread much of this report, and it's astounding how robust it is, and we are still on the path. It's quite amazing. So with Stuart, it's all about physics, friends, and particularly students. He was very fond of his students and nurturing them. He's always a socialite, and this is from a party a couple of years ago, and you can see he's always socializing. He was a very social person, loved to be in the company of other physicists, and especially young ladies. This is my daughter. I forgot to mention last night, I often speculated the reason maybe I said that before, that he liked to talk to my wife. Anyway, Stuart has indeed influenced us all. Here is the KamLAND collaboration at a collaboration meeting in Sendai where we were all there, and you can see that everyone really enjoyed their company quite a bit in this collaboration. I think the outlook is there have been many important discoveries in neutrino physics in the last decade or so. Much remains to be done to complete the picture. All you need to do is read Boris and Stuart's report. The students, colleagues, and friends of Stuart will continue the work he was so proud of, and also carry on the tradition of enjoying the company of each other, and I think this meeting is a perfect example of that. I just want to end with some thanks to some people who sent me some photos. So thank you very much.